This talk is part of a series presented by the TechAide AI4Good conference and hackathon. Our goal with this virtual event is to highlight technological innovation driven by artificial intelligence and directed towards beneficial areas such as health, environment, accessibility, and human rights. Importantly, we also aim to raise money for Centraide, or the United Way, a nonprofit dedicated to fighting poverty and social exclusion. And this is where you can help. Please consider donating by clicking the link in the description of this video. Any amount will be greatly appreciated. Also, if you're watching this before November 12, 2020, consider registering to our event for a chance to ask questions and interact with our speakers. This event would not have been possible without the help of our sponsors such as DeepMind, Ubisoft, Ivado, and Dell Technologies. We thank them for their generous support. Please visit our website for a full list of sponsors and partners. Finally, I'd like to give a special shout out to one of our sponsors, Ubisoft. For those of you who don't know yet, Ubisoft La Forge is a collaborative space created by Yves Jacquier. At Ubisoft Montréal, they bring together experts from their studio and from the academic sector to accelerate research and development through prototyping, complementing academic learnings while testing the potential benefits of technological innovations in virtual worlds and filling the gap between theory and practice. I invite you to visit their website, laforge.ubisoft.com, where you will find articles from the researchers and videos showing their prototypes. With that, I'll leave you to enjoy our featured presentation.
Hi, everyone. Thank you for inviting me to this virtual conference. I'm Olivier Corradi. I'm the founder of Tomorrow, and today I'm going to speak to you about electricity map and about assessing marginal carbon emissions in an electricity network. So I'm going to share my screen here and showcase you my presentation. There we go. So shortly about myself, I'm actually half French, half Danish. I've been studying in both countries. In Denmark, I've been studying mathematical statistics, and in France, I've been studying general engineering. I've been working a lot with the integration of fluctuating renewables in the electricity system. I worked with those topics at IBM Research. Then I was at Google, joined a French AI startup called Snips, and founded Tomorrow now almost 5 years ago in 2016. And the reason I did this is basically I got tired and fed up of seeing big corporates swallowing all the best minds of our generation to optimize on ad clicking. And I thought, what happened if we could really get all those smart people to work in climate change? Because it is really the most challenging issue of our generation. We've seen the world wake up to it as lately, for example, California has been burning literally. So hopefully Silicon Valley wakes up to this and we'll start seeing some meaningful change. Our mission as a company at Tomorrow is to get the world to understand and reduce their carbon footprint. We're doing that with two products. One is Electricity Map, where we help the world understand the carbon footprint of the electricity usage worldwide. And then another one, which we'll be launching by the end of the year, called Bloom, that helps companies track their carbon footprint across all verticals and take meaningful climate action. But today we'll be talking mostly about Electricity Map. So the obvious solution to climate change is that we need to electrify everything. Why? Because all of our energy emissions come from fossil fuels. And in order to replace fossil fuels, oil, gas, and coal, we're basically saying, wait, let's just electrify everything. Let's have electric planes, electric ferries, let's have electric heating, and so on. And that will have fixed everything. Unfortunately, we tend to forget sometimes about how clean that electricity is. And unfortunately, nowadays, still 30 to 40% of all the electricity worldwide is produced using coal. And you can see, for example, here an excavator that is getting coal from a mine, and you can see here just the tractor gives you an idea of the scale of this humongous machine. And I think what we've just forgotten as humans is the scale and the size of the operations needed to have me being able to record a talk right now with the light bulb and the electricity on, and so I don't see all the machinery that's behind it. Just having this picture for me makes me humble, and it mind blows me to see how many resources are used on this. So shortly about Electricity Map, I'm going to showcase a small demo so we're all on the same page about what it is. So Electricity Map is freely available on electricitymaphere.org. And what it showcases is close to real time. If I were to use a kilowatt hour of electricity from the system in my power plug right now, what would be the associated carbon emissions? So here I can, for example, zoom on Denmark. And you'll see, if I click on Eastern Denmark, where I'm currently located, you'll see here that for each kilowatt hour of electricity I consume, I would emit 134 grams of carbon. You see that my electricity right now is 88% low carbon. It's 78% renewable. And why the difference? Well, basically because low carbon also includes nuclear. And you would tell me, wait, that's weird because Denmark doesn't have any nuclear. Yes, but you see this arrow here showcases that some electricity is actually imported from Sweden to Denmark. And if I click on Sweden here, you'll see that there's a large portion, like a quarter of electricity available in Sweden that comes from nuclear. So electricity map enables you to understand the mix of the electricity both produced, exported, and in the end consumed in a given country. And you can zoom out here to see the whole of Europe. We actually have more of the world that's covered here. And what is fascinating about electricity map to me is that in the beginning, when we built electricity map, it was only built with a couple of countries on the map. Most of the map was gray. What happened is that we had contributors coming to the map, realizing that countries were gray, knowing about availability of data sources. They would then code a pull request that would fetch this open data, put it into electricity map, and then our carbon model on top of it would then determine which color we should be putting on the map and updating it automatically. And I remember a contributor telling us, it feels like taking a brush and just painting over the world because there's so much data available and it wasn't visualized. So that's pretty cool. So let me get back to the presentation here. And so electricity map has had a pretty big impact as an open source project. We've had more than 1,000 contributions over a couple of years. That has led to covering like big portions of the world that you just saw before. We have 5,000 daily active users, which is pretty amazing given the fact that we never spend a single dollar on marketing. It's been published and we've written pretty cool blog posts about what you can do with this data. And I'll talk a little bit about what we can do with this data afterwards. And it's also been used by ministers, heads of states. It's used by the European Parliament, the European Commission, for example, as well. So we are lucky to be engaging at policy level as well in order to make meaningful change here. So how does this work? We use the so-called flow tracing to compute the origin of electricity. So what we say is every zone is a copper plate. Electrons are instantaneously mixed and perfectly mixed. We're saying that the imports, they impact the consumption mix proportionally to the amount imported. So this means that if you're importing 50% of electricity in your resulting mix, 50% of the origin of electricity comes from that imported mix. And the last piece, I'll move my video a bit down here. The last piece is we don't choose what we export or what you import, meaning that if you have a green electron in Denmark, when you are exporting it to another country, you can't choose to export specifically that electron. You just export electricity and you get just a statistical average of whatever you export. And that's important because you can't direct individual electrons in the network. So this starts to create like a huge amount of data. And you can see here on this data visualization that we did, how the hourly data animates over time. So this is an accelerated time lapse, as we call it. And you see how Germany, for example, is oscillating in color between day and night as the solar panels are producing during the day, but not during the night. And you can see countries like, for example, Spain and Portugal that really become greener as the wind starts blowing. And the patterns, you can see the weather patterns are actually wind patterns. So when you have like a lighter color in the ocean, for example, that represents a stronger wind pattern. So how do we trace back the origin of electrons based on the rules that I just mentioned before? So what we need to write up is an energy balance equation. So what we say is power consumed in a zone, it must have been produced somewhere else. And the same accounts or holds true for CO2. So what we need to find here is the carbon intensity for each zone, meaning for each kilowatt hour used, what is the associated carbon emissions? And that's in blue. So if we look at the conservation of energy equation, we're basically saying, everything that's consumed in one area is the sum of everything that's produced. So there's some wind energy produced, some solar energy produced, and so on and so forth, plus the sum of the imports minus the sum of the exports. So far, no rocket science. Then let's switch over to conservation of carbon instead. So we're saying the total amount of carbon needs to be conserved. So everything that is emitted due to consumption must have somewhere been emitted due to production somewhere else. So if we break down total emissions in a given zone by how much power is consumed, with an average carbon intensity in blue, which is what we're going to want to solve for here, we can break it down and say that's equal to a scalar product, a sum of each production mode multiplied by the carbon intensity of that mode. So we're saying that all the emissions caused by local production are basically the sum of everything that's produced by wind multiplied by the carbon intensity of wind plus plus the production of coal multiplied by the emission factor or the carbon intensity of the coal emissions. And then you sum that up with all the carbon intensities of the imports. And remember here that we said that when you import electricity from neighboring zone, you will import that electricity with the carbon intensity of that other zone. And this is why I wrote carbon intensity here, but in a different color, because it's not the same as the carbon intensity here. This one here is the carbon intensity of the current zone, and this one here is going to be the carbon intensity of a zone from which you import electricity from. And then lastly, the last contributor to that equation is you need to subtract all the exports emissions. And here again, when you're exporting electricity, you're exporting it with the carbon intensity of your own zone, because you can't selectively choose to export only the good stuff or only the bad stuff. So in the end, you end up here with an equation which has multiple unknowns. You have unknowns for your own country, you have unknowns for other countries, and you can write one balance equation per zone. In the end, if you write one equation per zone and you put this up in a linear system of equations, a matrix, you can rewrite that as a matrix of coefficients multiplied by an unknown vector x, and that would be the blue here and brown unknowns that we have here, equals b, and b would be some constant that if you rearrange this equation, I haven't done it in this slide, you can rearrange it to write it up in this matrix form where you have an a and a b. A being the factors that represent the topology of the network, the graph, if you will, of connections in a topology. And so when you solve that equation, you end up having the carbon intensity as a solution. And this is in the end the color that is depicted on electricity map. And this gives you some interesting aspects, because you can also solve it not only with carbon, but also by origin of electricity, so with the different modes. And you see that, for example, in Denmark, the origin of electricity in consumption ends up having, for example, some nuclear energy here, which is imported, but also some hydro energy imported. And it's quite interesting to see, on days where there's a lot of wind, we don't rely that much on nuclear and on hydro, which comes from from Sweden, for example. But on other days here, you see there's a very big piece that comes from hydro. So Denmark, in a nutshell, is balancing its electricity system thanks to imports with neighboring countries, and hence why it's so important to have this flow tracing. Now to the crux of the problem. We're looking at the marginal origin of electricity. So if I plug an electric vehicle at home and I charge it, where would that extra electricity come from? It won't come from all of the power plants generating a little bit more electricity. What will happen is it will be the cheapest electricity, the power plant that is the cheapest and that has spare capacity will be the one that produces that marginal, that extra electricity that will go into the or that I have caused and that will in the end go to my EV. And this is why what you're doing in order to solve this is that you're ranking all of the different production systems based on cost. That's called the merit order. And the electricity system is meeting its current demand at this point here, for example, which would be coal. And then we're saying, okay, if you ask for a little bit more electricity, you will consume, in this case, a little bit more coal, because the coal is the system that is able to give that last demand in the end. And the problem is this curve, this merit order is secret because it's market sensitive information. So the question is, using machine learning, can we figure out where that marginal origin of electricity comes from? So to summarize, the color of an electricity map is the footprint of the electricity consumed. And the marginal origin of electricity, or the marginal footprint, is a sensitivity analysis. It means, where does the next unit of power come from? Like, how does the electric system react when I'm asking a little bit more electricity? Typically, the way this is done is in a static way, where we basically say, we're looking at historically from 1 hour to the other. Every time there's been a change in local generation in the system, we're tracking that in the left-hand side of the equation as a vector here of delta x. So those are all the changes in local generation. And then we want to relate them to changes in local demand through a given factor here, which we call the marginal emission factor. And so if on the left-hand side here, you have emissions, so changes in hourly emissions, and on the right-hand side, you have changes in consumption, the marginal emission factor will tell you every time there's been a change in local demand, what is the associated intensity in terms of change in local generation emissions. And that's called the marginal emission factor. The problem is it doesn't take into account imports and exports, and that's because it's based on local generation. It doesn't take into account external effects that are independent changes in local demand, so we'll see that a bit later. And also we have no hourly granularity in the sense that this G factor is just a constant factor. So just tell me, on average, when I'm increasing my local demand by 1 kilowatt, for example, then we are increasing emissions by 200 grams per kilowatt, for example. And that's, of course, insufficient. So a better way to do this is to look at a more dynamic model here. So we're breaking things up a little bit more here. So we'll say every time there's been a change in the system, the change can happen because of two different components. One is changes that are independent on changes in local demand, and one is changes that are dependent on local demand. So let me explain that a little bit further. What happens is when, for example, the wind starts blowing, the carbon intensity of the system will go down, but not due to a change in demand. There's no causality. It's just correlation. It just turns out that the wind production will change the structure of the mix. And we need to separate that out from changes in the mix that will really rely on the fact that I put my electric vehicle to charge at a given time. Another way to say this is that when I'm plugging my EV, there's no way that the additional electricity can come from wind, because there's no way that the wind turbine can be turned on from my actions of plugging the electric vehicle. And that's a really tricky part to establish mathematically. So the mathematical intuition behind that is also to say that we're looking at a sensitivity analysis around a preferred operating point. And that preferred operating point can be represented as, business as usual. And we can call this a fixed point in the system. And we're calling the first order Taylor expansion so this is the fixed point. This is what happens here. The f of z is what happens if we don't change the system, if we don't consume more from the system. And then there's a departure from that fixed point, which is my actions as a person. For example, I put my EV in. How does the system change? And this change in the system is characterized by G. And we parameterize that function with a parameter Z, which represents all of the features, all of the all the features of a machine learning model that would enable us to characterize this gene in a dynamic manner hour after hour. So this is the overall methodology, and we can write a linear model for F and G, which are written up here in a very, very, general sense. What we do then is the Z vector here is a vector with, more than 500 features. So what happens is that for each zone in this Z vector, we would put all the weather conditions of the current zone. We would put the weather conditions of the neighboring zones as well. And we put a lot of other market specific information, such as the price level of the different zones and so on. And once you solve, so basically we're trying to fit a model through this equation that solves for the Z here. And because there's so many features, we need to select the relevant ones. And this is why we're using L1 regularization in order to reject all the features that are useless. So let's look a little bit about the results here. So we're applying this methodology specifically to the generation mix here. So we're saying, let's reconstruct, here again, we can say here, I go back to the equation, let's reconstruct all changes in local coal generation, local hydro generation, and so on for each country with this sum here, and let's see how well we can reconstruct the total signal. And this is the plot that you have here, for example. So you can see this is in France, and this is the hydro, changes in hydro, this is DG hydro, changes in generation of hydro, and the hat is the fit of the model. So we see it works pretty well. And then going back to the previous slide, what I'm really interested in is, once I've made sure that it fits well, is to extract this part of the equation here, because this is the sensitivity analysis. This tells me the marginal effect. And here you can see the marginal effects on the local generation. One example that I like to point out is, for example, France here. You can see that on average, there's this color here that corresponds to nuclear. So on average, the French system is actually getting balanced with nuclear. Nuclear is sometimes on the margin in France. There's a, what is it, like 15% chance that it is on the margin. So we're actually getting hourly values out of this, but here I'm just showing the averages over time. We can do the same thing with interconnectors, but this starts to become much, much more tricky. So with the interconnectors, we're basically saying, what is the change in imports from a neighboring country as I'm increasing or decreasing my consumption, for example, my electricity consumption. And here again, you can try to refit a signal, and you see just the level of noise we're dealing with here. And then you can visualize here the marginal effects in a matrix. And you can see, for example, here in Denmark, in DK2, the eastern zone that we have, we can see here there's on average an interconnector is getting solicited as you are, or is getting used as you are changing your consumption. So with the two previous examples I showed, you can plot on the diagonal the changes of local generation. So that's Denmark with respect to Denmark. That's just the changes in their own local consumption. Local generation. And then you have the off diagonal turn, which showcases the changes in imports. And then what you can do here is, because the imports only showcase you a first order information, they basically show in Denmark, how is Sweden affected by Denmark. But you can't see, because of the effects in Denmark that are having consequences in Sweden, which might have consequences as well in Poland, you want to tie the knot and say, what is the consequence of Denmark on all of its neighbors, not only the immediate neighbors, but also the neighbors of the neighbors of the neighbors. And using the same methodology, slightly differently, that the flow tracing method that I explained in the beginning, and unfortunately I don't have time to explain it here, you can compute the nth order matrix. So the example you can see on the left side, this is only first order. It just looks at one country and the impact on its neighbors. And then the matrix to the right showcases you the one country and the impact on the rest of the grid. And you can see some pretty interesting things here, where some dots here, for example, in this area start to appear. You have other ones, for example, here, this is pretty empty. And you start having here a lot of zones that are appearing here. and I think this is, for example, Finland and Norway. So you can see there's probably one interconnector through which Norway is connected to Finland, and then that means that in the end, all of the Norwegian zones are impacting Finland somehow. So that's a pretty interesting way to use machine learning and then to use this matrix expansion to then figure out what is the consequence on all the countries of doing something in one country. And then you end up having, as a conclusion, some pretty interesting things like Finnish marginal electricity in Denmark, you can see here, or hydro marginal electricity in Denmark. So I won't go too much into the details because unfortunately I won't have time in this presentation, but I find that's pretty fascinating. And remember, this is an hourly view. So here in blue, you have the carbon intensity of Eastern Denmark. This is basically the color on electricity map. And in orange, you have the marginal carbon intensity. And you can see how dynamic this signal is. There are some times, for example, around here, where the marginal electricity is low carbon, probably because the imports we're getting are from low carbon countries, such as Norway. And you can see in the other areas here, the marginal is actually higher. So it's the extra electricity we're getting is probably for peaking plants, gas or worse, and that increases the carbon intensity compared to the average, for example. So this is pretty neat. I will jump over this slide. So what can you do with this data? One thing is you can figure out when to charge your electric vehicle. Another thing you can do is also to figure out where to install the next unit of renewables. So what's interesting is if I install a wind turbine in a given country, when that wind turbine is going to produce electricity, it is going to replace an existing system. And that existing system it's going to replace is exactly the marginal power plant that we discussed before. So for example, if you install a wind turbine in Norway, odds are that you will probably reduce your hydro consumption at the time where that wind turbine is producing electricity. So what's the net benefit in terms of carbon? You probably haven't won that much. And this is why it's at the end of this graph here, because this graph shows annual avoided emissions for each kilowatt of additional capacity that you would install. On the other side of the spectrum, you have a country like Poland, for example, where you're guaranteed to remove coal power plants or dirty generation if you install clean intermittent renewable. And this analysis is actually done hour by hour, is following the actual production of a wind turbine based on the weather patterns that happened in, I think it's 2019 on this one. So that's pretty interesting as well in order to make sure that we invest money in the right places and install wind turbines in the right areas. I'm nearing the end of my presentation, so I just want to say all this data is available through an API that we developed on api.electricitymap.org. So feel free to visit it and contact us if you want to work with us on this topic. I'll showcase another example here where we're super proud to talk about our partnership with Google, where Google is utilizing our data to make sure that their data centers are using electricity at the times where the sun shines and the wind blows. Basically, they have a lot of flexibility when they use computing power, especially when you have to train an AI model that has to train overnight. They're even luckier because they can also pick the place in which the computations should run. So that's pretty interesting use case right there. And the last thing that I want to say here is that it's part of the Bloom Climate Action Platform. So we're launching this new product called Bloom, which will enable companies to understand their carbon footprint. And if that company has a smart meter, they will be able to connect it to Bloom and get access to exclusive electricity data through Electricity Map and be able to set optimization and different progress tracking initiatives. So if you're interested in knowing more, head up to bloomclimate.com. That's nearing the end of my presentation. I wanted to thank a lot the organizers for creating this, and also wanted to encourage you to look at the link in the bottom of this video. Please donate as their support to support the work on fighting poverty and social exclusion. This is the reason why this event happens. Thank you again for inviting me, and if there's any question, write them down in the comments and I'll be happy to answer them.